Alright folks, Unit 3, Day 1. Today we are going to talk about finding limits and what that means. Basically, the first day this year we're actually going to talk about calculus-y things. So let's get into it. Let's sketch this graph and then let's write an equivalent function with a modified domain where we take out the whole. Now this looks kind of silly, because if you look at it, well, it's just f of x, the function x plus 7, the linear function, except if you think about this second factor here, x minus 4 over x minus 4, well, that is essentially just creating a whole at x is 4. So we're going to modify this and say x cannot be 4. So to graph this function, draw some axes, it's just going to be the function x plus 7. So 1, how am I going to do this? Look, I got all fancy, I got some axes. So again, this is just going to be that line with a slope of 1 and a y-intercept of 7. The only difference is going to be that at x equals 4, so let's see, 1, 2, 3, 4 up here, I have a hole. So I'm going to draw that as an open circle at that x value and then connect it. So that's what this graph is going to look like. It would look exactly the same as that original f of x function. These two f of x's say exactly the same thing. We're just modifying that hole, taking it out. That's why a hole is called a removable discontinuity, because you can take it out of the function and just modify your domain. Everything else looks exactly the same, because for every other value other than 4, that function, that fraction there just equals 1, so it doesn't do anything. But the question is, what would be the value of this function if we didn't have that hole there? Well, think about what y value we'd be going to when x was 4. Well, we had it drawn there before, we just erased it. It'd be that dot right there. So we've got an x value of 4, and then a y value of 7, 8, 9, 10, 11, which makes sense also that it's 11 if you think about x plus 7. 4 plus 7 is 11. So even though we know our function doesn't exist there, we do have a hole, we can think about how if, well, we didn't have that hole, the value of the function would probably be 11 at that point. Well, guess what, folks? You just found a limit. That's all a limit is. It's talking about what y value your graph is heading towards for a specific x value. So here we can say that the limit as x goes to 4 of f of x equals 11. And I know that we didn't really do anything super complicated, but this basic idea where a function is going actually has huge consequences for calculus. It is the backbone of calculus. And so we are going to spend this unit exploring limits and their properties a little bit. So let's look at this function now. F of x is given to you as x cubed minus 1 over x minus 1. So notice that we have a hole at x minus 1. If we wanted to factor f of x, we'd end up with, in the numerator, x minus 1 times x squared plus x plus 1. Because that is a difference of cubes, and that's how difference of cubes factors. If you didn't remember that, you could do synthetic division. You could divide by the linear factor x minus 1 by using the solution of 1 and writing your cubic function x cubed, 0x squared, 0x, and 1, and then just synthetically dividing. And you get a lot of 1s, if you notice. Except that last one up there should be negative, so when we get that one, we get a remainder of 0, and we get 1, 1, 1, which is x squared plus x plus 1. And again, this is over x minus 1. So again, I could rewrite this as f of x equals x squared plus x plus 1 for x not equal to 1, because we have a hole there. It is undefined at that point. So Otherwise, though, this function is going to behave just like x squared plus x plus 1 behaves. So we can say that the limit of f of x as x approaches 1 is 3, because if you look at our graph, as we're going up to that point and as we're coming down to that point, we are hitting the y value of 3 right there. So you can tell by looking at a graph what the limit of a function at a specific point will be just by looking at where it's going. If I wanted to find the limit as x goes to 0, well, look at the x value of 0. My graph is going to that point right there, which is positive 1. So I could say that the limit as x goes to 0 of f of x is positive 1. That's really all a limit is saying. They obviously get more complicated, but that's the basics of it. But here's the kicker. You may have noticed on the last side I drew 2 arrows there. I said as we approach it from the left, it's going to 3, and as we approach it from the right of that hole, it's going to 3. And that's why the limit existed there. Compare that to this graph. Let's talk about the limit as x goes to 0 of f of x. Well, if we look at the limit from the right side, so if we look at the point we're trying to find the limit of, x equals 0, if we come to that point from the right, so while moving left on our graph, we can see that our y value there is clearly going to a y value of positive 1. So I can actually write down the statement, the limit as x goes to 0, and then I put a little plus right there, and that plus says from the right. So the limit as x goes to 0 from the right of my function f of x equals 1, because that's where my graph is headed while going to the point x equals 0. From the right, I'm up at the y value of 1. But if you look at the limit from the left, so from the left moving to the right, well, my graph is going to the y value of negative 1 right there. So I can say that the limit of f of x as x goes to 0 from the left, and notice to say from the left, I have a little superscript of a minus sign. That limit is negative 1. Notice that the left-handed limit and the right-handed limit is different. From the right, I'm positive 1, and from the left, I'm negative 1. Therefore, my limit does not exist. So I can say the limit does not exist. And for a limit to exist, the limit from the left and the limit from the right have to both exist and be the same value. So let's look at those next 2 questions. Does the limit as x goes to 1 exist? Well, look at the x value of 1. We're talking about our graphs up here. So from the left and from the right, both of my limits are heading to that y value of 1. So yes, that limit does exist, and it's equal to 1. Same thing for a limit as x goes to negative 1 of f of x. Negative 1, I'm heading to this point right here. From the left and from the right, I'm heading to the y value of 1. So yes, that limit exists, and it is equal to negative 1. Whew. So let's look at this function then. F of x equals 1 over x minus 5. It's our favorite rational function, shifted to the right 5. So let's think about whether or not this limit exists. Well, remember what we said. For a limit to exist, you have to be heading to the same value from the left and from the right. So notice I've got my asymptote here. If I follow this graph from the right to the left, I'm following up that tail, and I'm going up towards positive infinity. So I can say that the limit of f of x as x goes to 5 from the right is infinity. Now if I look at my graph from the left, so from the left moving closer and closer to the right to that point, I am going off towards negative infinity. So I can say that limit as x goes to 5 from the left of f of x is negative infinity. Notice they disagree, so our limit does not exist. Compare that to this rational function, where both of my tails now are going up. So now if I take my limit from the left, I'm going up to positive infinity. If I take my limit from the right, I'm going up to positive infinity. So my left and right-handed limits agree, so I can say that the limit as x goes to 5, and notice when I don't write a plus or a minus, it's talking about from both sides. The limit as x goes to 5 of f of x exists, and it is positive infinity. So now look at this weird situation here. We have this piecewise defined function f of x that is just the boring straight horizontal line for all x values not equal to 2. But for the one specific x value of 2, our function is defined as having a y value of 0. So, to answer the question, what is f of 2? Well, f of 2 is the value of the function at 2, and it's defined as 0. So f of 2 is 0, but that does not mean that the limit of f of 2 is 0, because the limit is telling you where your graph is headed. And by all accounts, this graph from the left-sided limit is heading right there, and the right-sided limit heading to that same point with a y value of 1. So the limit of f of x as x goes to 2 is different from the value of f of 2. The limit is 1, and the value is 0, so that tells you that this function is discontinuous. If the limit of a function and the value of a function at a point agree, then your function is continuous at that point. So now let's look at tables. We can estimate limits numerically using tables. So if we want to find the limit of f of x, and we have a table of values for f of x, we want to find the limit as x goes to 1. So look at the table from the left-handed limit. So x values less than 1 that are getting closer and closer to 1. So again, reading it from the right over to that value of 1 right there. Look at your f of x values, aka your y values. It sure looks like they're getting closer and closer to 3. And then if you look at the limit from the right as you go to the x value of 1, well, those also look like they're getting closer and closer to 3. So we're going to say that the limit as x goes to 1 of f of x equals positive 3. So you can create your own tables of values to do this, to evaluate the limit of functions using your calculator. But if you are entering a function like x squared minus 3x plus 2, do not forget your parentheses. So you have to go parentheses x squared minus 3x plus 2, close your parentheses, divided by, open a parenthesis, x minus 2. If you leave those parentheses off, you will absolutely get the wrong answer. So enter that function into your y equals screen, and then once you do that, hit the second button and the window button. That will get you to your table set options screen, and this is where you choose values. So I would recommend setting your table up like this for that function, since we are going, if you notice the denominator there is x minus 2, that's a big hint that you're going to be looking at the x value of 2. So go ahead and set your table up like this. I did 1.995 as my starting table value, because I want to see values to the left of 2 and values to the right of 2. And that little delta table there, the little triangle with the table, I set that to 0.001, so I'm looking very close to my function at the x value of 2. Do that, you will get the table that looks like this. Notice we have an error at 2 because you are dividing by 2, so it is undefined there. But if you look at your y values, from the left, they're getting closer and closer to positive 1 from the underside, and from the right, they're getting closer and closer to positive 1 from the upper side. So we are going to say that the limit of x squared minus 3x plus 2 divided by x minus 2 as x goes to 2 equals positive 1. Yay! But if you're filling in a table like this from the book where they give you a bunch of different values, you got two options. You can either set the option on your table set screen to allow it to ask for x values, and then you can type them in. But what I normally do is I will graph this function. So I'm going to graph it. It's going to look exactly like this. It's going to go parenthesis, square root, and then if you're on 83, it'll do that parenthesis, 1 minus x, close that parenthesis, minus 2, close that parenthesis, divided by parenthesis, x plus 3, close your parenthesis. So if you do that, I'm just going to graph it on the window. Look at your values there. I'm just going to go from -2 to 4. It doesn't really matter, but I'm going to go -2 is less than, it'd be helpful if I could do things. -2 is greater than, x is greater than -4, like that. So a min of -4 and a max of -2. And then go to your graph and hit trace, and then just go to those x values there. So I'll let you do that yourself. I'm being lazy. I don't feel like doing it. But you should find the limit. So I lied to you. I found the values anyways. But from this table, it certainly looks like the limit of this function is going to be -0.25. So again, I can say the limit of our function, the square root of 1 minus x minus 2 over x plus 3 as x goes to -3 is -1/4. So let's go ahead and hit this closure real quick. We got some functions and graphs here. Let's go ahead and look at number 7. Finding the limit as x goes to 3 of this function. Well, as x goes to 3 from the left and from the right, I'm approaching the same value, which sure looks like it is positive 1. On this graph, limit as x goes to 1. Again, my limit from the left agrees with my limit from the right. It is going to the value of positive 3. Over here, our piecewise defined function, as x goes to 2, our limit from the left and our limit from the right are both going to positive 2. Don't be fooled and write 0. F of 2 equals 0, but that is not the limit as x goes to 2 of f of x. So finally, last point, as x goes to 1 from the left, it agrees with the limit from the right, which is going to the y value of 3. So again, limits, it's all about where you're going, not what you actually are.